If you recall, yesterday we wanted to get our calculus thinking and adapt our calculus thinking to functions of two variables, eventually equations of three variables, eventually equations of more variables. And then eventually we're going to be parameterizing things because like we mentioned yesterday, one of the things that we're going to have to describe is a one-dimensional curve in three-dimensional space. That's going to require parameterization. So we had talked about the two big questions of calculus, how they were stated for functions of one variable and how we can modify them for functions of two variables. So the first one. Oops. Starting with a function of one variable, classic Calc 1 and Calc 2. The first question, what is the slope of the line tangent to curve at given points? What is the slope of the line tangent to a curve at a given point? We're phrasing these questions, we're thinking about our answers from the context of a one-dimensional curve in R2. We know that the slope of the line tangent to the curve at a given point, we're going to use the derivative to find the slope. That's how we get at the direction. So our equation will be y equals, nice. Y naught plus the slope, which is f prime at x naught, times x minus x naught. To write a linear equation in two variables, I need a point and a slope. We get the slope from the derivative. Change in y with respect to x. If we upgrade our function, to a function of two variables, now instead of having a one-dimensional curve in R2, we've got a two-dimensional surface in R3. So if we pick a point, we're not going to put a line tangent to it. We don't just have a line tangent to the curve. We can have a whole plane tangent to the curve. So if we let let z equals a function of x and y, that is, if we upgrade to a two-dimensional surface in R3, then the question gets upgraded. So first of all, we got the slope in service of getting an equation, so we could have a linear description of the function near the point. So for a function of two variables, we're looking at a surface in R3. So if we pick a point, we're not going to just put a tangent line at that point. We're going to put a whole tangent surface at that point. This makes sense because linear equations in three variables make planes, where linear equations in two variables make lines. And so we're really just trying to create a linear approximation of the function near the point. We end up with two different slopes, but we saw how these slopes operate in previous examples. We have linear functions. The slope in front of the x is how z changes with respect to x. And the slope in front of the y is how z changes with respect to y. Looking at the parallels between these two things, looking at the parallels between two questions, the original and the upgraded question. The delta y over delta x was a derivative. So this delta z over delta x and the delta z over delta y are going to be derivatives. But there's two of them for one function. So these are future derivatives. Which is the same thing that we did before, because it is always the same thing that we did before. The second question was a little bit trickier. So we're going to break it down and look at the specific things we need to see. The second question was the area under the curve question. What is the area under a curve and above an interval on the x-axis? We know how to calculate this. The area will be the integral from a to b of f of x to x. We want to think about where this comes from and what this expression is telling us. We also want to think about why we have to do this calculation, and we can't just do area is length times width. So once again, the story of the integral, the story of the definite integral says finding area. There is but one way to find area, and it is the very idea of area. Area is length times width. That's it. All the other stuff that you know about area, 1/2 base times height, pi r squared, all that stuff is just niche solutions to individual trivial problems. The concept of area is a distance multiplied by another distance covering area. It's just a description of what area is. Length times width. And that's what we're calculating in the definite integral. The f of x is the length above the x-axis, and the delta x is the width on the x-axis. We're calculating length times width at all these values of x, and then adding up the results. That's the concept of the definite integral. It's exactly based on area. So this is length. The reason that we have to do this is that stupid length is not constant, so we can't just multiply. It's variable, so we have to add. It's continuously variable, so we have to continuously add. Continuous addition is definite integral. So we have a length times width, and we're evaluating that length times width at all the values of x from a to b. That's what the integral part is telling us. Calculate f of x dx, area, length times width, at all those values of x, then add the results. We do recognize that this part where I say add the results is a little bit messed up. You're like, oh, this is a continuum. Where do we put the plus signs? And the answer is quiet, you. We have limits for that. And that's where the weirdness of calculus happens. In between, where we write the Riemann sum as I goes from 1 to n, where we're putting all the plus signs down. And it's like, well, now let n go to infinity. It's like, oh, well, where do I put the plus signs? Because it's no longer discrete, it's continuous. And we're like, oh, magic. Those are magic hands, not jazz hands. They're different. Magic. I wonder if I always should rewrite this class as like an 80s magic show. And come in here with a sparkling tuxedo, some music is playing.
The average person isn't probably not because like a magic show, they don't understand it.
It would be, yeah, it would be perfect. Go on Penn and Teller, fool us. And then we do this. They're like, well, we didn't take math. So I guess I won then. Plot twist, Teller has a PhD in math. So what we want to do is we don't just want to know how to calculate this because we have a shortcut for calculating this. That's where the magic happens. We want to get at the thinking because we need to adapt this to a function of 2 variables. Now, the good news is that when we look at a function of 2 variables, z is equal to f of x, y, z equals f of x, y is still going to be telling us the height above the plane, but it's not going to be doing it over just a boring ass interval where x starts at a and ends at b. We're doing this at a bunch of points x and y. We're calculating the height at a bunch of points x and y. So this function is still just meters of height. But like most of you guessed yesterday, we went up by 1 degree. So area plus 1 is volume. We're going to be getting a volume, and that makes sense. If I draw a volume over here, if I make an umbrella, there's a certain amount of volume underneath it. The umbrella itself has an area, but underneath it is a volume. So here the question becomes, what is the volume under the surface and above a region in the XY plane? So that's the adapted question. We're calculating a volume under a surface. When we say under a surface, we're going to have a bunch of XY. That's going to be some kind of region, some kind of area. So our volume will be some kind of integral of f at x and y. That is still going to be a height, but we're going to need an area to make a volume. Height is 1. I need a length and a width. I need 2 more to make a volume. So this is still height. Even though we're plugging in 2 variables, it still only counts as 1 dimension. That's called the Gimli rule. Still only counts as 1. So what we need to turn this into a volume is an area. So I'm gonna write this dA, and that's gonna be our area. When we do this integral, it's not just gonna be an integral over a bunch of x values. It's an integral over a bunch of x values and y values. It's over a bunch of x, y. So I'm gonna say the integral over R. R is a bunch of points x, y that we're plugging into this expression, then we add the results. Same thing that we always do with the integral. Because in math, as we go forward, we're just doing the same thing. So R is a bunch of x, y. We evaluate f at x, y times dA, whatever the heck that is, at all those points that we're using that are in the region R, then add the results. What we want to get at is that there's the thing that we're calculating over here, height times area, and the integral is telling us where to make that calculation. In the area, length times width is area. This is the area calculation. The integral from A to B, that's telling us where to make that calculation. Once we have that, integration is easy to apply. Because length times width is just one version of multiplication. Another one that's popular in calculus classes is distance is equal to rate times time. Work is equal to force times distance. What other ones did you do? Force is equal to pressure times area. Make things continuously variable. Any questions? So what we want carried forward today, first of all, is the overall impression that we're just doing the same stuff with more variables. I want you to upgrade area under a curve to volume under a surface. I want you to recognize that under a curve, we have an interval, which is easy to describe. Under a surface, we'll have a region, which is complicated. It can have all kinds of different shapes. The structure of the integral is the same. Make this calculation f of x dx at all these values from A to B. Make this calculation f of x y times dA at all these points R. R is just a collection of points x, y. How's everybody okay? Everybody looks stunned. I've been talking for almost an hour, so it's my superpower.
Okay, so I think we can do an example. I think we just take X, Y, 2.
Yeah, we do. We're not gonna get one today.
Okay.
I'm just murdering you all with words today. I'm like Black Bolt, but it takes a lot longer. I'm sorry, I should have sent me instead of Black Bolt in the movie, the multiverse movie. Well, what are you gonna do to me? It's like, well, Leach is gonna talk about calculus. Oh, well, okay, sounds kind of interesting. And then I start talking.
There's only three available concepts.
No, I just do the same thing. I just use my soothing voice. What is the equation of a plane? Tell me the surface. And I play some Enya music in the background. Everybody chills out, falls asleep. How's everybody okay? All right, that's going to do it for today. So big news, of course, first practice test next week on Thursday. It's going to be on vectors and vector operations and linear equations in R3. That's it for today. Think about calculus and then let that run in the background. Everybody have a good day, and thanks for playing.
Calculus is